there's like actual digital meters, total suspended solids, temperature releases, or oxygen potential. We can have online monitors on the pipe that's going out into the environment. So in the case of sewage treatment, though, it's interesting. We can have, these are the major pollutants that are dealing with like sort of biological health. But if you want to do these more rare pollutants like heavy metals, pharmaceuticals, these trace chemicals, there's no digital online meter for these. There's no inline thing that's going to measure trace amounts of mercury, trace amounts of antibiotics that are coming out of your sewage treatment plant. Not only can you measure it infrequently, but it's a lot more costly. So we're only visiting, we're only able to take these measurements once in a while, a lot less measurements, a lot higher cost. So even within, total suspended solids. So these would be key measurements of pollution that are just measuring like how much of the biological load do we get out of what the sewage treatment plant polluted. If we want to get measurements of some trace chemicals, it's a lot harder to get that. So it'd be a different monitoring regime. And I talked about this a little bit before in monitoring in the transport sector. So if we have power plants, we have one single place. We have sewage treatment plants, we have one single place. In the transport sector, all these polluters are all throughout, everywhere, on all the roads. So we don't have a way to measure emissions from individual cars. We don't have data loggers on cars saying how much they're emitting it. Maybe we will someday. I mean, the cost of sensors keeps going down. But what we do is we go to the smog check station, as I said, every couple of years. If you sell the car, you need to get it smog checked. You probably had this come up for you guys. You need whoever's running the smog check station to be honest, right? It's very easy for people to be like, can I just pay you to pass my car smog? So it's all computerized. There's a computerized set of certificates. We do things so that we take the human factor out, so that the smog check can only pass. The guy can't influence the smog check, and then he can't just give you the stamp on your registration. It has to be submitted electronically. There's a whole bunch of things thinking about how this disaggregated checking millions of cars will be less and less able to be gained. And there's a whole separate area for emissions for trucks, and there's a whole separate permitting sector. We have a lot of other things that we do for transporting cars. We do, these fuel economy standards are a separate whole thing than these emission standards. Gas stations have a whole bunch of emissions control, so you have to, control where the pump is, sucks all the air out. We have recycled vapor traps on our vehicles. We have a whole bunch of other things just besides the tailpipe. So tailpipe is some share of the emissions, but in NOx, there's a whole bunch of other things that you don't really see, right? That you don't see as a consumer, but there's checks and balances on the gas station, on parts of your car. There's the check engine light. So one big thing that they did was now the check engine light in your car comes on when your emission system isn't working. Your catalytic converter isn't working, the check engine light comes on. A lot of people will be like, I don't really care if I'm polluting, I just want my car to run well, right? But when the check engine light comes on, people will take their car to the mechanic. So they've sort of got all the automakers to agree to have the check engine light come on when the catalytic converter's not working. So we have, in all these different cases, a whole broad sort of science moving forward on monitoring pollution and monitoring environmental effects. So we have, on the pollution side, on the receiving pollution side, not on the tailpipe side, we have a whole bunch of ways that we can sample ambient quality over time and get good data, better and better data, more and more sensors out there of air quality, water quality. I don't know if you guys have heard of this one, but there's a famous thing in China, the Chinese government in Beijing. Beijing's becoming one of the most polluted cities. And the Chinese government releases very censored data on what the air quality in Beijing is, because there are international standards of what's safe to let children out of the house, what's safe to let old people outside, and these keep getting violated in Beijing. And so the US government put a air quality monitor, like a robotic device, on the roof of the embassy, and it's set up to automatically have a Twitter feed. So if you live in Beijing, you can just check the Twitter feed of this robot that's telling you what the particulates are in Beijing that day, and like whether it's safe or whether how dangerous it is. And it's really frustrating the Chinese government because they're trying to release these numbers. They're like, oh, today the PM 2.5 is under 100, when it's really 300, and it's like unhealthy to actually do exercise outside. So there's a whole thing where our ability to get this information is only increasing. We're having more sensors, we're having more more deployment of these things, and now that it's like it used to be you would have to find somebody who was doing air quality measurements and find their spreadsheets, and now you're checking Twitter and you're seeing in real time what the ambient air quality in Beijing is. And now we have a whole bunch, definitely people in this building, we have remote sensing. So we have satellite data. I've already showed you pictures of the Gulf of Mexico and the dead zone in the Great Lakes, right? So that's like we have an ability to show ambient water quality in the Great Lakes and show that dead zone changing over time. Look at it. So we didn't have that historically. That's new that we're getting more and more information from remote sensing. The ozone hole, so this is a hole up in the stratosphere over the Arctic, right? So we've launched whole satellites to measure this. They were doing infrequent flights. This was an issue in the past, but this is really remote, far away thing. We can barely conceive of where this is happening. But now we have more and more. We have visualizations. You can look at pictures of how big the ozone hole is growing and getting smaller over time. So we have more and more of this monitoring. And now a big one, global climate change. We look at YouTubes and videos of how big the ice sheets are, how many glaciers are caving off, how close are we to ice sheets melting. And this is like sort of like our tipping point of climate change. We have sensors there. We can see how much ice there is. This is the sea level rise question, right? So we have climate change happening. We have Arctic ice melting, and it's all with sensors now. It's all like real-time data showing us what this season is going to look like in terms of sea level rise. Just saying, we have a whole bunch of satellites up there measuring different types of air quality, different types of radar, different types of frequencies. We have more and more information on ambient quality. So we've already talked a bunch about the Clean Air Act and nitrous oxides on the East Coast. So this is looking at how air quality has been cleaned up from the satellite. This isn't from measuring on the ground. This is like now we're looking down from satellites and seeing, here's where everyone lives, and here's the pollution getting better, less of this really high levels of pollution. Interestingly, this is also a thing where technology developed in the first world is leapfrogging to developing countries. So this is a project that, just as an example, from the European Space Agency that's in South Africa, where there's some big pollution here, and they can use the satellites. European Union can send their satellites over, pick up some pixels, do sort of ambient air quality studies. They can go on the ground and do some studies to sort of truth what their pixels look like, and they can know, how air quality in South Africa is being affected and model it and graph it and sort of know how to target things. So it's interesting in the cases of developing countries coming forward, they might not have as much abilities to regulate in terms of like regulatory structure, but they have a leg up in terms of like the technologies that are available. So we think about our regulator question and what are the violations going to be? So what we're going to say, you can pollute this certain amount, but we want to put a penalty for you polluting over this certain amount. So one of them is, for a plant, a Chevron refinery, is number of hours that you're polluting over some sort of standard. So we say that in time, the number of hours that you're out of compliance, right? And you can also say what quantity you're over the standard. So we're going to allow your factory to pollute 5,000 tons, and last year you polluted 7,000 tons. We're going to put a penalty on the amount that you went over the standard. You have an oil spill, you're allowed to spill some small amount as sort of doing business and loading and unloading your tanker. But this time you had a big spill, and we're going to quantify that, and we're going to fine you based on what the size of your spill is. And then you're going to have some sort of threshold level of what triggers the penalty, right? So your Chevron refinery is allowed to be out of compliance, for 2 hours a day or 23 minutes a week or something like that. You're allowed to spill a certain amount of oil as long as you have some sort of treatment system to clean it up. But then over this certain amount, we're going to trigger a penalty structure. Over a certain amount of spilling, of polluting, we're going to trigger some sort of penalty. Your wastewater treatment plant is allowed to spill a certain amount, is allowed to leak a certain amount over the course of a year. What we have with sewage treatment plants, that's a big one, is when it rains. So when it rains, they get overwhelmed and there's big spills out in sewage. Don't go swimming after it's been raining. I'm sure that you guys all know that. But if you look at water quality in the Bay, in the LA Bay, it's just really bad a few days after the rain, and then it's basically clean again after that. So we're going to put a penalty if you're exceeding a certain level, exceeding a certain time. But we're going to set levels that are going to trigger a sort of penalty and regulation. There's a story in the book about diesel trucks. So they were out of compliance. There were some regulations on what the emission standards were going to be on diesel trucks, and the manufacturers were violating them for years. They weren't violating them a little bit each year. They were violating them a lot year by year by year. So then the regulator has to put fines, has to put how much we're going to make companies pay. So mostly in this class, we're starting out, we're like, let's tax pollution overall, right? Let's tax just quantities of pollution. But are we going to scale those fines to be related to something? We're just going to use them as a price to get to our efficient level of pollution. A lot of times that we would say we're going to have some part of the fine go to the cost of cleaning, cost of mitigating some sort of damage. You had some pollution in the marsh, we're going to do some marsh cleanup, and so we know what it costs to clean up oil damages in marshes, we know what it costs to contract environmental scientists that are going to go out there and do this mitigation work, so we're going to scale some sort of penalty to our cleanup. We also have a schedule for natural resource damages, so we have values to the environment that we have existing. These are coming from different lawsuits and different environmental economics estimates of like what it costs to preserve environment, we're putting values on lives of turtles, right? We're like, how much was the value of the tortoise in the desert for the electricity plant? So we have values on, we want to conserve more nature or we want to preserve more nature. We have values on you've polluted and harmed that nature somehow. We also have punitive damages. Punitive damages is more like we want to make it hurt for you, the company. This isn't something that's just from environmental economics. We have this a lot. You hear a lot about punitive damages in sort of consumer liability cases, right? We don't want McDonald's to make the coffee too hot so it spills on people. We want to make sure that McDonald's does the right thing. It doesn't make coffee too hot, it doesn't spill on people. So we're going to have really high damages so that they remember to not make coffee too hot. We don't want Exxon to be spilling in Prince William Sound, so we want to make sure that they don't do that. We can add punitive damages on there. Most of the cases we're going to operate on the top line, but then when there's big cases of big pollution or gross negligence or sort of companies acting deceitfully, you get to these later punitive damages or natural resource damages. The cautionary tale, so we talked about in the contingent valuation case, I showed you and walked you through this big oil spill, the Exxon Valdez spill in Prince William Sound. And we worked together, we did this sort of estimate, what would people be willing to pay? You voted on your phone, what would be willing to pay for these damages? So it got to a jury, they were rewarding natural resource damages. Crazy tale though, the $5 billion was an estimate that partly came out of cleanup costs, partly came out of natural resource damages, and partly came out of this contingent evaluation survey, what would people be willing to pay? What was the value to people of this huge pollution incident? Exxon Valdez has a lot of lawyers and a lot of money to pay a lot of lawyers. And they kept waiting and they kept litigating and they took it to every possible court. So the original jury ruling in 1994 was $5 billion. Then it went down to $2.5 billion in an appeals court ruling. They got a whole bunch of the different charges thrown out. They got all the way to the Supreme Court, waited a long time, and they got the whole thing reduced to a $500 million payment, of which they had already paid out and already cleaning the beaches up, right? So $5 billion is what the jury said, and $500 million is what the Supreme Court said 14 years later, right? So we have regulators, we have regulations, we have people litigating on behalf of the environment, but then we have big companies with a lot of lawyers to sort of avoid paying this environmental burden. So here we go into chapter 13. We're thinking about enforcement. So we want to put incentives on the firm. The regulator has some incentives. The firm has some sort of incentives. And we want to make sure that we have the costs to the company, making them get to the efficient level of pollution. We want to have the cost of them exceeding this pollution standard, the cost of their penalty. We want to compare that to their marginal cost of complying. And we want to make sure that we structure the cost in the way that we get the right amount. And then we're going to look at statistics a little bit and this term expected value. Expected value implies probability. Probability of getting caught. Probability of enforcement. So we can write a regulation. We don't know whether it's going to be enforced, whether our monitoring system is going to catch us, whether we're going to get caught by the regulator, whether any fine is going to be put in place. So here's chapter 13. There's a graph here for a polluter. So here's our marginal benefit curve that we've also had in the homework. Also had the first 3 graphs with these marginal benefit curves. So if there's no regulation, what happens? This is the homework question in all 3 homeworks. Where are we polluting with no regulation? So out here we have this point. That's like something like 17,000 tons of pollution. In the chapter 13 example, we have a regulator who decides, all right, we need to clean this up. We need to get to 5,000 tons for your power plant. And we can see from the marginal benefit curve for this company that corresponds to a $1 per pound cleanup. So we're going to say you're allowed to emit 5,000 tons. You're currently emitting 17,000 tons. So the first thing to see is the penalty needs to be greater than this amount here. The penalty has to be greater than $1 per pound. I hate when we're using pounds. We should be using kilograms. So we have this area, though, this area under the curve that we look at also in the problem set. That's the amount that the company is sort of giving up by reducing their emissions that much. So we have $5.9 million it's going to cost them to clean up to this level. They have a cost of cleaning up. That's about $6 million worth of costs. They're reducing emissions by 11,000 tons, and it's costing them $6 million to get there. So we need to think about whether, when we're putting our regulation, to make sure that the costs need to be higher than that. So the book starts out, we're going to put a fine. If you go over 5,000 tons, we're going to put a fine of $1.50 per pound. For every pound that you emit over the 5,000 tons, that's our threshold. 5,000 tons you can emit and pay no fine. For every pound that's over 5,000, you're going to pay $1.50 per pound. So your benefits are much lower than the cost that you're going to have to pay. So that's why we need to make sure that our fine is higher than the dollar that the benefits are. If we had set some number down here, then the fine would be less up to this point. The fine would be less. And so we'd rather just pollute, pay the fine, and we would still be getting some benefit from, even if we had been paying this fine. So the fine has to be higher than our marginal benefits curve at the point that we want them to stop polluting. So in the real world, the company needs to think about the expected value of the penalty. So we can diverge a little bit here and think about statistics, think about probabilities. You guys taken statistics? Yes? Are you going to take more statistics? Take more statistics. It's totally worth it. It's one of the great things you can do in college. It sucks, but it's totally like a useful tool. The world runs on statistics. Economics runs on statistics. Biology runs on statistics. Environmental science runs on statistics. If you can, take more stats. It's totally worth it. All right, so here we're just going to do a little bit of statistics for the people that are not that familiar with it. So we're going to think about the probability for this polluter being caught times the cost for them to be being caught. The expected value, I'm going to walk through this a little bit, is the sum of each outcome times the probability of each outcome. So here's a little math writing here. The expected value is the probability of each outcome times the value of each outcome. So we can say the sum over all of the probabilities of each outcome. The integral of some distribution function times these outcomes. We're not going to do this complicated integral, but we just need to think of, in our case, it's the penalty, how much we would have to pay for polluting, times the probability of being caught polluting, plus no penalty, so we don't have to pay any penalty, times the probability of not being caught. So we have multiple states here. So in any case, our expected value is the probability of outcome 1 times the payoff. Let's say the payoff. There's different ways we could say that. Times, well, let's just say outcome 1. It could be positive or negative. Times outcome 1 plus probability of 2 of outcome 2 times outcome 2. And then we would sum that up for all of the different possibilities, right? Our probability is a percent. It's the chance. It's the chance of something. So they're going to sum to 1. The probability of all the different states are going to sum up to 1 by construction. So if there's only 2 possible states, there's 50% chance of each of these, which we could say is 0.50, right? 0.5 times outcome 1, 0.5 times outcome 2. The outcome we have to think about as a few different things. If it's a fine, right, it's a minus amount of dollars we have to pay as a fine. If we're gambling, right, we paid a certain amount of money to play the game, we could say it's a payout. How many chips did the casino give us back, right? If it's the stock market, we could say it's the return. You know, we have a 50% probability of the stock market going up a certain amount, 50% probability of the stock market going down a little amount, so we would have some sort of return on our investment. So we have uncertainty, we have multiple possible states with different probabilities to them, we have multiple different ways we'll think about the outcome. In this chapter, in chapter 13,